Just really quickly looking at forms of power generation. Traditionally in Australia, we've used hydro, the Snowy Mountain scheme, the Snowy Mountain Scream as well, but the Snowy Mountain scheme is hydroelectric, where I used to live in the area. They've just got a whole series of dams. There's the second reservoir. That might be Talbingo, there's Tumut, then off it goes off to the Murrumbidgee. So they've got a series of pipes. Each pipe's about the diameter of this room or bigger. So pipes that are about 10 metres round. They have got, from memory, about 8 to 10 running in parallel with a height drop of 200 metres. Power behind that is mass flow rate times the pressure. The pressure is 200 metres. 200 metres. So the pressure equals pressure naught plus rho g h equals 1,000 times 10 times 200. It's 2 megapascals of pressure, holding 20 atmospheres of pressure at the bottom of the pipe, going into a turbine. A turbine is just basically a fan or a pump impeller that is connected to a generator. So down the bottom here, we have got this massive amount of powers, pressure times flow rate. Massive pressure, 20 atmospheres. How much water flow do you think there is in 10 pipes, each about 8 to 10 metres diameter? Probably a fair bit.
Good amount.
A good amount. So we've got a good amount of power. The Snowy Mountain scheme, I think from memory, is 2 gigawatts. Okay, when it's all turned on. Okay, so this is good for 2 reasons. One is you can turn them off quickly when you need short-term power for the system, because the generators only have got to make as much power as the country needs that second. They cannot make any more power than the country needs this second. If you make more power, then they've got nowhere to store it. Yeah? If you don't make enough power, then you're not getting 240 volts, you're getting 220, 230. And motors stop working very well. Yeah? So they've got to physically match the power generation to what the country needs. Hydroelectric's great because it's immediate turned on, turned off. Yeah? So, I'll just finish off the drawing. Down here, we've got a fan. There we go, one of the world's worst fans, but anyway, connected to a generator. And off it goes. So here we are, we're generating electricity. It gets generated at 330 kilovolts. It gets generated at really, really, really high voltages. So you've probably seen the transmission towers that are about 20, 30 metres tall that look like this. Where you've got this almighty gap between the electricity wire and the ground. That's to avoid it sparking out. If you, because the cables have got a catenary loop, I don't know what the distance is, 15 metres say. If it's any lower than 15 metres, then on a rainy day or a humid day, you will get a spark thrown from 330,000 volts to the ground. Make sense?
Yeah.
Not good, especially if you're walking underneath it at the time, because you are the highest point and that's where the sparks go to. There's a reason why you're not allowed to build near a high voltage power line. Aside from the fact the electromagnetic radiation permanently isn't good. If you Google Richard Hammond putting fluorescent light bulbs vertically underneath a high voltage power line, he just buries one in the ground and the other end actually picks up enough voltage to make the fluorescent light bulb glow. I'll put a link in the video down the bottom there. But physically, there's an electric field around the wire. Why do they send it at 33,000 volts? Quite simply because when you transmit electricity down a cable, it's just the same as your heater at home. You put 240 volts in, heat comes out. You put 330 volts in a power cable that you want to send to a consumer, you don't want heat to come out. Yeah? Power, P, power, equals current times resistance. Yeah? Equals voltage times power equals current squared times resistance equals voltage times current. Yeah? If I send this through at 330,000 volts, then the current is very low. If I put something through at 240 volts, I'm sending through a lot higher current, aren't I? And the current is what makes the heat. Yeah? So they send stuff down at 330 kV just to minimise transmission losses. Just to recap really quickly for power generation, I was happy enough with the description of power generation. There are multiples. As I said, hydro is used because, and it's still valid today, because that covers the short-term peaks and the troughs. The hydroelectricity as well. If they're running short of power storage and hydroelectricity in the dam, they will pump the water back up at night time. So they can basically recharge the water back up into the top reservoir and save it for later on when they need it. So if the water's low in the top dams, they'll use coal-fired electricity to pump the water back uphill, just so it's stored later on for when they've got to get electricity back again. Hydro, solar. As you know, solar produces DC electricity. Every house is producing DC electricity off the solar panels, those that have one. Problem they have, the entire network is timed to produce the AC power at exactly the same frequency, 50 hertz, with the peak plus 240 volts sitting in the line at exactly the same time. Every house is basically pumping electricity back in, and it's physically got to match. So it's DC, it gets rectified back to AC, not rectified, converted to AC using an electronic box, which then has to go physically, and every house has got to hit the peak at the same time when it's feeding the electricity back in. So the box, the converter, is physically measuring the peaks and the troughs, and it's physically matching what the house is producing to what's in the line that it's feeding into, if that makes sense. But solar power is great for daytimes. Solar power is not so good for nighttime. Yeah, so it's can be stored in a battery. You can make DC, store it in a battery DC, and then turn it into AC power when you want it in your house at night time. But it's not the world's best fix unless you've got mega banks of solar panels and massive amount of batteries to keep your house going at night, or else your fridge might run out of electricity at 2 AM. That's the issue with solar. It's great for daytime peaks. It takes the load off coal in the middle of the day. It's about 5% of the country's total electricity in the daytime. Nighttime, it's 0%. Make sense? Mm-hmm. Coal is simply light a fire under a boiler, boil water, make steam, feed the steam into a turbine. There's our beautiful turbine again. Connect it to a generator. And out it goes. It takes a lot of time to get the boiler hot. You can't really shut off steam to a boiler because then it just builds up enough pressure so it explodes. So once the boilers are hot, they take a while to cool down. So the coal is a base load, solar, hydro, cover the peaks and the troughs in the daytime. Solar basically sits there as a daytime peak load, hydro backs it up. Wind power is another form of renewable energy. Once again, you can sort of control the wind turbine. You can feather the blade, so instead of it facing the wind, so it's turning, if you turn the blade so it's parallel with the wind, the turbine stops spinning. You can shut them down, which they do in a gale. They physically lock the turbine still, lock the blade still for that reason. They're your sources of energy. As far as power generation, that's that. Let's have a look now at power transmission.